Hey everyone. Today we're going to take a quick look at a gas law problem and an equilibrium problem and see how the two kind of fit together. Um, we'll do a standard equilibrium problem, but first we're going to use the ideal gas law and Dalton's law of total pressures to give us some of the information we need to solve that equilibrium problem. So once again, I'm going to remind you that this is the ideal gas law. Pressure times volume equals the number of moles times the ideal gas law constant times the temperature in Kelvin. And usually what we do is we're using this to find N, number of moles, or we can use it to find the number of grams if we know the molar mass, or we can work it the other way. And if we have grams or moles, we can kind of work it into this. So we'll take a look at that here in a couple seconds. I remind you that this is Dalton's law of partial pressures. And what we're saying is if we have a mixture of gases, for example, 3 gases or more, the total pressure of this mixture of gases in a container is the partial pressures. That's what these P's are for. Partial pressure of each gas combined. Okay, so that's pretty easy. More importantly, though, we know that the partial pressure of a gas, say gas A or gas 1, would be the moles of that gas in the mixture divided by the total moles. We call this the mole fraction. So it's the moles of that gas over the total moles times the total pressure. And we'll use this here when we flip over and do the problem. Okay, I invite you to do this with me with the problem that I posted. So let's take a second to read the problem here. It says 100 grams of solid A are placed into an evacuated 5-liter flask and the temperature is raised to 400 degrees Celsius. So we put some of this solid into the flask. There's nothing else in there. There's no gases. And we know that this solid is turning into these two gases. And at some point, the reverse reaction starts to happen and they reach this equilibrium. So this is a reversible reaction. And when the equilibrium is reached, the pressure in the flask is this, 285 kilopascals, and there's still some solid remaining. So that's important because this is telling you that the reaction did not go to completion, but that there is a lesser amount of solid now, probably less than 100 grams. We're assuming we used up some of that to produce those gases. And whatever gases were formed, the gas B and the gas C have a total pressure of 285 kilopascals. Okay? So we're going to go ahead and do a few things with the gas and the solid that are here. This is very similar to a solubility problem where you have a solid and two aqueous ions in solution. Okay, so it's very similar. First thing we're going to do is calculate the partial pressures of each of the gases. So we're going to use the mole fraction again and say, all right, I created these two gases in a 2-to-1 ratio. Okay, and Dalton's law of partial pressures says that we're going to take the moles, in this case, the moles of gas B. So we have 2 moles of gas B for the 3 moles that were produced. Okay, so we're producing 3 moles of gas for every 1 mole of this. Now, we don't know exactly how much of this was used, but we know it's a 2-to-1 ratio. So 2 moles of gas B were produced for every 3 moles of gas, right, total products. And that's what we call our mole fraction. And that comes out to 66.667% times the total pressure, 285 kilopascals. Okay. And we're going to do the same thing with gas C. Now, gas C is 1 mole out of the total 3. So 1 mole of gas C for every 3 moles of gas total in the products times 285 kilopascals. And again, this is keeping in mind that the solid is still there. It's not really affecting the pressure at all. All right, so when we do that, we get 190 kilopascals for the partial pressure of gas B and 95 kilopascals as the partial pressure of gas C. Okay. So again, just using Dalton's law of partial pressures to understand that whatever we produced is a combination, is a sum of the partial pressures of those products. Now we're going to take a look at part B. It says calculate the total moles of gas in the flask. Once again, we produced some product that is now here, right? And we know it's a 2-to-1 ratio. We don't know exactly how many moles are in there because we don't know exactly at what point equilibrium was reached. In other words, how much of this solid was actually used, how much of that 100 grams. So this is where the ideal gas law comes to the rescue, because we know that the number of moles is a relationship between the pressure, the volume, and the temperature. So let's go ahead and plug some numbers in that they gave us, remembering to use our units. So the pressure is 285 kilopascals. The volume, if you remember up here, was a 5.00 liter flask. N is the number of moles of gas in the flask. And at this point, it's just products because we didn't have any gaseous reactants. R, this would be moles. Oops. And R is our ideal gas constant. And that is 8.314 liter atmospheres. Liter kPa mole Kelvin. And remember, you don't have to memorize that. You'll have your formula sheet that'll tell you whatever R value you need based on the units of pressure. And of course, our temperature is 400 degrees Celsius, which we know we need to turn that into Kelvin. So we add 273, and that comes out to 673 Kelvin. Okay. I'm not going to do the math online. However, we are going to find out that N equals 0.255 moles of gas. Okay, and that is gas B and gas C together. Okay. Now we're going to go ahead and do the actual equilibrium part of this problem, and we're going to go ahead and calculate K sub C for the system. And again, we haven't changed the temperature, so it's at 400 degrees Celsius. So as we know, K sub C is going to be the concentration. Let me put the reaction up here. Concentration of anything, any gases or aqueous reactants or products. So in this case, it's going to be the concentration of product B squared times the concentration of gas C, which is also a product. So products over reactants, and because the reactant was a solid, there's no denominator here. So that's what we're going to do here. And what we're going to say now is we're going to kind of go back to this mole fraction that we had and said, all right, we know that these 0.255 moles of gas, this is our total. And 2/3 of that, or 2 moles out of 3 moles of that, is gas B, moles of B. And then 1 mole out of those 3 moles is times that number of moles is moles of C. Okay, so what we're going to do is take these moles of moles of B and moles of C and divide them by the volume of the flask. Okay, so I'm going to do a lot of math here, but really what we're just saying is, look, I know how many moles of B we have in that flask, so it's basically going to be 0.667, that's 2/3, times the total moles of gas, 0.255 moles, over the 5 liters, right? Because again, we want this to be a concentration, moles over liters. And we're going to square that. Again, this 0.667 represents the mole fraction of the gases in that flask at equilibrium. And then we're going to take the concentration of C. We know that 1/3 of that gas, because of this 2-to-1 ratio, 1/3 of that gas is gas C. So 0.255 moles. And again, that is in a 5-liter flask. That has not changed. And that is not squared. Right? And we're going to multiply this all together to get K sub C. And we get 1.91 times 10 to the minus 5 as K sub C. Okay, so that tells us, if we look at this, that this reaction is pretty heavy on the reactants, not big on producing products at 400 degrees Celsius. Obviously, at other temperatures, it will have a different K sub C. So unitless there. So just to kind of recap here, we know what the mole fraction of these gases is, and we know how many moles of total gas we have. And that allows us to come up with concentrations for each gas, which we can then use to find K sub C. So just to kind of go back to where we started, where does the ideal gas law, or the gas laws in general, intersect with equilibrium? And usually it's using the ideal gas law to work out the number of moles, and perhaps using the Dalton's law of partial pressures, particularly these mole fractions, to figure out what's the number of moles for each of the gases. Not every problem will be like this, but if you know how to use your ideal gas laws, that kind of gives you a little jumping off point for a lot of different types of equilibrium problems that involve gases. If you have any questions, see me after class.